Now we shall talk about the conversion of galvanometer in voltmeter. Okay, that is a voltage measuring device. Now this voltmeter is used to measure the potential difference across any section of the circuit. So galvanometer now we want to use as a voltmeter to measure the voltage across any section of the circuit. Now see, this is the arrangement. Try to understand. You have this galvanometer. Now originally this is the galvanometer which you are having. So galvanometer is having its own resistance which is Rg. Okay. Now you want to convert this galvanometer into a voltmeter. Now whenever the voltmeter is joined across any 2 points in the circuit, okay, it is joined first of all in parallel. So ammeter, if you want to join, then it must be joined in series in the circuit, and the voltmeter is joined in parallel across any component whose potential difference you want to measure. So parallel connection must be there, that of this voltmeter, and current passing through the voltmeter must be ideally zero, or we can say resistance of the voltmeter must be very high. So the galvanometer, which is having around about 50 to 100 ohm resistance, that resistance has to be increased significantly, and its resistance must be ideally, try to understand, ideally must be infinity. And for ammeter, the resistance of the ammeter must be ideally zero. Okay, so this resistance of the galvanometer has to be increased, or we can say ideally it must be infinity. So for this, the first of all voltmeter has to be connected in parallel with the section of the circuit of which we want to measure the potential difference, and voltmeter must draw a very small current, and the current will be very small when the resistance of the galvanometer is very high, that you can understand. So the galvanometer's resistance must be ideally infinity, or we can say it must be very high. Now for that we have to connect a large resistance, that is capital R, in series with the galvanometer. Now try to understand the galvanometer first of all. Galvanometer is like this. It has its own resistance Rg. Now you have to connect another resistance capital R whose value is very high in series with the galvanometer, so that the combination which we have made, this combination which I have marked with the circle, that combination behaves as voltmeter, okay, and its effective resistance becomes very high. Okay, so this way it has been done. Originally the galvanometer was like this. Okay, it has its own resistance, but this external resistance is connected, and now this becomes the combination which is known as voltmeter. The resistance of voltmeter is now, originally it was having Rg. Now you have connected this external resistance R, which is very high in comparison to this Rg. So effective resistance will be about or almost equal to the external resistance which you are using. Try to understand, if the galvanometer has its own resistance Rg to be 50 ohm, and if you are adding say 2000 ohm from outside, that is your R, okay, this is Rg. So effective value will become 1050. It is almost equal to 1000 which you have connected from outside. Approximately we can say it is equal to resistance which we have joined from outside. It is very high, ideally infinity. Okay, the scale of the voltmeter is calibrated to read the voltage value easily. The scale of the pointer which is moving on a scale, that scale must be calibrated. It must be written properly, 1 2 3 whatever is required value, okay, so that the value can be read easily. Now we define voltage sensitivity as deflection per unit volt. Okay, now we have this equation which we have already derived. Okay, phi is equal to NBA upon K into I. Now if I divide both the side by voltage V, so that is done here. Okay, phi upon V, and it is I upon V. This is I upon V. Okay, I upon V. Okay, now phi upon V is equal to NB upon K. Now V upon I is R, so this becomes 1 upon R. Okay, so I upon V has become 1 upon R, inverse of resistance. So required value of resistance to be connected in series. So this gives you voltage sensitivity. Try to understand this formula is nothing but the equation of voltage sensitivity, that is deflection per unit volt. Now how much resistance should be connected, that is the big issue. Now that is not discussed in our textbook. Say galvanometer is there, its own resistance is there, so this whole arrangement is a galvanometer. This is galvanometer. Now how much resistance is to be connected, series resistance with this galvanometer, that can be given by this equation. R is equal to V upon Ig minus Rg. V is the voltage which is to be measured, Ig is the current capacity, and Rg is the resistance of galvanometer. So if the value of Ig, that is current capacity, is say 1 milliampere, okay, so it becomes 1 into 10 raised to minus 3 ampere. Okay, and voltage which you want to measure is 1 volt, and the galvanometer has resistance say 100 ohm. Okay, this is the value of galvanometer's resistance. Then you can easily calculate the resistance which is to be connected. Okay, and that R is equal to V is 1 upon 10 raised to minus 3 minus 100. So it becomes 1000 minus 100. So 900 ohm resistance has to be connected in series with the galvanometer to convert it into the voltmeter, which can measure the voltage of 1 volt. Okay, here Ig is current capacity of galvanometer. Okay, means current for which the galvanometer shows the full scale deflection. Rg is the resistance of galvanometer. Okay, now these are certain notes. Now if you want to increase the current sensitivity, it will not necessarily increase the voltage sensitivity. There is an example for this discussed. Current sensitivity is given by this. Say phi upon I is NBA upon K. Now N is made 2N. If you make the value of N to be 2N, then this phi upon I will become double. So current sensitivity is getting double. That is easily understood. Okay, now the resistance of the galvanometer is also likely to be doubled as the number of turns are becoming double. Try to understand, when you increase the number of turns of the coil of the galvanometer, then the resistance of the galvanometer is also likely to be doubled as number of turns are becoming double. Say you have 5 turns and you have used say 10 centimeter wire. So if you make say 10 turns, then you use 20 centimeter wire, naturally the resistance is going to become double. Okay, so it is discussed here, the resistance of the galvanometer is also likely to be doubled as the number of turns has become doubled, since it is proportional to the length. As you know, resistance is directly proportional to length of the wire. Okay, so as you know that it need double the wire to make the turns double. Okay, so phi upon V, try to understand, if you make phi upon V, that is voltage sensitivity. Okay, then this, say for example you are doubling the length. So you are doubling the length means now the number of turns are doubled. So N becomes 2N. You have doubled the turns. So resistance will also be double. It becomes 2R. So instead of N, now it is 2N. and instead of R it is 2R, so phi upon V remains as it is, or we can say voltage sensitivity remains constant. Okay, as you increase the number of turns by doubling it, then resistance also simultaneously is getting doubled, therefore the value of this phi upon V is going to remain constant. Okay, so watch these videos 2-3 times, try to understand, write in your notebooks, keep the notebook open, textbook open. Okay, here we are completing the chapter number 4. Okay, thank you very much.